All right, hello, Physics 11. We are now working on circuits part 4, and today we're going to be discussing electricity or electrical energy and electrical power in circuits. So far this unit in our first three classes, we've introduced a few different quantities and units. So one quantity that we have dealt with so far is charge, and we know charge is measured in coulombs, capital C, and I mean, if we're talking about what exactly a coulomb is, I guess one way of putting that is it's the amount of electrical charge that would be contained in 6.25 times 10 to the 18 electrons. So just to give us an idea of how much charge it is, that's how much charge it is. We've also talked about potential difference or voltage, roughly the same thing, and we have 1 volt as our unit. This is equal to the amount of energy. So 1 volt means that there is 1 joule of energy for every coulomb of charge. So we've kind of discussed it when we talked about our analogy of the log ride at the PNE. We've sort of said a volt is how much energy you would give to a packet of charges. So if I have a 1 volt battery here, for example, it means that every coulomb of charge that's moving in this direction is going to have 1 joule of energy. So if you were to pack together 6.25 times 10 to the 18 electrons and combined with that package, you give them 1 joule of energy, that means that it's gone through a 1 volt power supply. So just another way of looking at that. We've also talked about current. So current we measure in amps, and 1 amp is equal to 1 coulomb per second, because we have this formula as well. We have that current equals flow of charge over time. Charge measured in coulombs, time measured in seconds, so coulombs per second is equal to 1 amp. And of course, we've also talked about resistance, and resistance is measured in ohms. And I guess you could say it's 1 volt per amp. So it means that if for every volt of energy, or for every volt that a battery has in a circuit, there means there's going to be 1 amp in the circuit. So 1 volt per amp is another way of looking at an ohm, but typically we just leave it as ohms. But we will see why these two here are going to give us a better definition of energy. And the clue here, you can see that obviously we're dealing with joules, and so we'll be able to see how these two quantities really relate directly. So we haven't so far talked about power or energy use, but we often do. When we're thinking about electrical devices, we might say this is a 5-watt bulb or a 60-watt bulb or whatever it is. So we talk about wattage, which we know is to do with power. We talk about that a lot when we're talking about electrical devices, but this can often be confused with energy or voltage. So remember what power is. Power is the energy transferred per second. And so we can think about it as like, it's not just amount of energy, but it's how quickly energy is transferred. So another way we could put this is the rate of energy transfer. Is it transferring from one thing to another, or is it transferring from one form to another? And how quickly is it doing that? So we can actually get a definition of power, or from our definition of power, I should say, and from Ohm's law, we can derive some formulae to describe electrical power. So the first one I'm going to give you is this. What I want you to think about is when we're talking about power or energy, in either way we're dealing with joules. So let's just start with our unit that has joules in it. So I'm going to describe 1 volt as equal to 1 joule per coulomb, and 1 amp is equal to 1 coulomb per second. Well, what would we get if we were to multiply 1 volt by 1 amp? So let's see what happens when we multiply 1 volt by 1 amp. This is the same as saying 1 joule per coulomb multiplied by 1 coulomb per second. Now you may notice that there's some canceling we can do, the coulombs, and so in this case here we're going to be left with 1 joule per second. Now what is 1 joule per second? That's correct. That was a little physics pun for you. Hopefully some of you caught that. Watt is 1 joule per second. Remember, so 1 watt is 1 joule per second. It's how quickly that we're transferring energy, right? Rate of energy transferred in joules divided by time it takes in seconds. So 1 joule per second is 1 watt. That's correct. Okay, so this is one formula that we have. If we want to talk about power, and power measured in watts is equal to current measured in coulombs per second multiplied by the potential, which is measured in joules per coulomb. And so if we multiply, again, we multiply the coulombs per second by joules per coulomb. Coulombs cancel out, and we have joules per second or watts. So this is our very first formula here. Power equals current times voltage. And so I'm going to put that one in this box here. Power equals current times voltage. Now, so we have this formula here. We've got this formula, the power above here, formula P equals I times V. And we also have Ohm's law, which says that V equals I times R. So how can we combine these two formulas? So we have P equals I times V, and we have V equals I times R. And I want you to combine those two to try and make two new formulas for power. So you're going to need to essentially substitute these quantities, some of these quantities that you can, into this formula above here. So please take a minute, pause the video, and try solving these two, try solving what the other two formulas may be. Okay, so let's give this a try. So the first one is probably the more obvious of the two. So I'm going to say P equals I times V, but we know that V equals I times R. So let's substitute that into here. We have P equals I times R. This is our V. We're taking the V out and replacing it with IR because those are the same. Those mean the same thing. And so what do we end up getting? We end up getting P equals I squared R. So this is our second formula here. P equals I squared R. And we just get that from putting that V equals IR into here. Okay, so this is the first one here. I'm going to put this one separate. And I'm going to make another one here. Now the other formula we have is we've taken this V and replaced it. So now let's try taking that I and replacing it and see what we get when we replace that I. So if P equals I times V, and we know V equals I times R. Actually, let me just move this up here. So V equals I times R. Then what is I equal to? So if we rearrange this for I equals V divided by R. So now let's take that and plug it into this formula here. So we have P equals I, but instead of using I, we're going to use this V over R. And we're going to multiply that by V, and then we can see here we get equals V squared over R. So this is our third and final formula for electrical power. So P equals I times V, P equals I squared R, or P equals V squared over R. So just taken Ohm's law and substituted in for the V, and then substituted in for the I, and we get these three formulas here. So let's try a few questions out. So an electrical fan has a resistance of 12 ohms and requires 0.75 amps of current to function properly. What voltage is going to be required to operate the fan? And I guess the follow-up question to that would be, what is the power going to be? Sorry, I should have written that down here. And find power as well. Okay, and then the second question, electrical heater emits 1 times 10 to the 2 watts, and so that's just 100 watts. Connected to a 120 volt power line, what is the resistance in the heater? So please pause the video here and try both of these questions. All right, so if you're just coming back after trying those problems out, let's figure it out for ourselves. So first of all, we've got this problem here. So electrical fan resistance 12 ohms, current 0.75 amps. Now to find power, we can actually just solve this right away because we have I and we have R, so we can use this formula here. So P equals I squared, so 0.75 squared, multiplied by R, which is 12. And so we have 0.75 squared times 12, and that's going to give us 6.75. So the answer to this is 6.75 watts. And there we go. And let's try for the voltage. So V equals I times R. So this is going to be 0.75 times 12. 3/4 of 12 equals 9 volts. And what you can see here is that you can, if you use any of these three formulas, because now we have P and we have V and we have, sorry, we have I, we have V, and we have R. So we could use any one of these three formulas. And we can see here that 0.75 I times 9 is going to be 6.75. We've already figured out that I squared R is 6.75. And if we go 9 squared divided by 12, we're also going to get 6.75 as well. You can prove that to yourself in your calculator if you want to do that. Okay, question 2. An electrical heater emits 100 watts, but it's left in this form, so you know it's 3 sig figs. When connected to a 120 volt power supply, or power line, what is the resistance in the heater? So in this case here, we know P, and we also know V, and we're trying to find out R. So this is going to be, we're just going to explicitly call it 100, this is going to be 120, and this is our question here. So if we want a formula that has these three, it's going to be this one up on the right. So P equals V squared over R. If I rearrange for R, I'm going to have R equals V squared over P, and that way R equals 120 squared divided by 100, and this is going to be, let's see, 120 squared divided by 100, and that's going to give us 144. So the resistance here would be 144 ohms. All right, so if we want to measure energy consumption or energy transfer, so power is how quickly energy is being transferred, or power equals energy transfer divided by time. What if we just want to find out energy? If we want to know how much energy we've used. Well, in this case here, we're just going to have to rearrange. So energy equals power times time. That's what we need to remember to figure out how much energy we actually used. If I use a 60-watt bulb for 60 seconds, so that's going to be 60 watts times 60 seconds. That's going to be 3,600 joules. Remember, 1 watt is 1 joule per second. So 60 joules per second for 60 seconds. I'm left with joules in the end here. Okay, and when you eventually have to pay your own energy bills, I know you're lucky enough your parents pay for it now, I'm sure, energy consumption is actually listed as kWh, or kilowatt hours. So this is a weird way of, like, we don't give energy bills in joules, we give them in kilowatt hours. But how many joules is in a kilowatt hour? So try and figure out that. What this formula does, if you can see here, this kilowatt is a measure of power, and then hours is obviously a measure of time. So they are having here power times time. Oops, power times time. Right, to get this formula here. So pause the video again and tell me how many, or write down, figure out for yourself, how many joules are in 1 kilowatt hour. All right, so hopefully you try this out for yourself. So 1 kilowatt hour, well, 1 kilowatt, so if energy equals power times time, in this case here, the power is 1 kilowatt, or 1,000 watts, and the time is 1 hour. So 1 hour is going to be 3,600 seconds. And so this is going to be 3.6 times 10 to the 6 joules. So if you want to know when you're being charged in kilowatt hours, you can just multiply it by 3.6 million, and that's going to tell you how many joules that you have used when you look at your power bill. So again, one more time, pause the video and try doing these 2 questions here. That's it for this lesson after these 2, so we'll finish these 2 up, and yeah, that'll be it for the week. So pause the video here, try these out. Okay, so number 3, what's the heat produced in a conductor in 19.6 seconds if there's a current of 13 amps and a resistance of 7.20 ohms? So something to keep in mind, if we think about, say you have an electrical stovetop, and what you've got in an electrical stovetop is that curl of metal, and that curl of metal is going to be essentially just a conductor. It's a piece of metal, which is what a conductor is. And as the electricity goes through there, all those collisions with the electrons smashing into the ions of the metal conductor, those all produce a little bit of heat. Same thing with a filament light bulb. You have those old style light bulbs before halogen or compact fluorescent bulbs. It's just a piece of metal that would get really, really hot. That's all it is. And in some cases, it would get so hot that it would emit light. But yeah, essentially, that's what's being produced. Is that it's just heat being produced, and if it gets hot enough, some light will be produced as well. So what is the heat produced in 19.6 seconds if a current of 13.0 amps is going through it and it has a resistance of 7.2 ohms? Well, we sort of need to, you can do this in 1 or 2 steps, and either way is going to be fine. So you could say energy equals power times time, and the power, in this case here, is we're using current and resistance. So this is going to be our I squared R formula. And so you could do this in 1 step and just say E equals I squared R times T, or you could do this in 2 steps. So figure out I squared R and then multiply that by T and do 2 separate equations. It's totally fine if you want to do it in 1 or 2. If you're doing it in 1 step like this, then you're going to have 13 squared times 7.2 ohms times 19.6 seconds, and that's going to be this value here. So I'm going to call this 3 sig figs 2.34 times 10 to the 4. And we're asking about heat, so it's going to be in joules. All right, now this one here, 150 joules of heat are produced in a conductor in 5.5 seconds, and we know the resistance. What's going to be the potential difference across the resistor? Well, let's try this one out ourselves. So we know that we have this formula here, energy equals power times time, and the power formula that we are going to use is the one that relates to, we can see here, we have resistance, and we're trying to find potential difference. So the formula that we want to use for power is going to be our one that relates voltage and resistance together. And so if we go back to our original 3 options, this is the one right here. So if we, I'm going to solve this one in 2 steps. Again, you could do it in 1 step, that's fine too. Let's do it in 2 steps here. So I'm going to solve for the power first of all. So we have energy equals power times time. And so if we're trying to solve for power equals energy divided by time, this is going to be 150 divided by 5.5, and that gives me 150 divided by 5.5. That's going to equal 27.27 repeating. Okay, so that's going to be my power, and I also know that power equals V squared over R, or in other words, V equals P times R, and then square root that whole thing, because that's going to equal V squared. We're trying to solve for V. So in this case here, if I multiply this by our resistance, so this is my P, I'm going to multiply this by resistance, 0.273 ohms. That gives me the V squared value. I'm going to then square root this answer here, and that's going to give me my V. So V in this case here is 2.73 volts. So V equals 2.73 volts. So if we wanted to solve this in 1 step, we would just put all these 2 formulas together. So we would say E, should do it in a different color. We could just say E equals V squared over R times T, and then V squared equals E R over T, and therefore V equals that. And you get the same answer either way. If you multiply 150, multiply by 0.273, divided by 5.5, take the square root of that, you're going to get the same value anyway. So do it in 1 step, do it in 2 steps, completely your call. A bit of a shorter lesson this week. Please enjoy working on the lab. It's really, there's not a lot of options for in-home labs. You don't have a lot of equipment. Hopefully all of you have a kettle. If you don't have a kettle, send me an email or a message and we'll figure out something else for you as a backup plan. All right, thanks very much.